Going live, Mike. All right, we are live. I apologize because this is my first YouTube stream on this account, so I had some configuration problems. But welcome to Rustling, Los Angeles. This is our first meetup in 2021 and also ever. Just a quick reminder that we are also on Rambly, which is a virtual conference room where you can have breakout sessions about tonight's talk and communicate with other attendees over voice chat. Tonight we have a great socially distanced meetup. Expect our next few meetups to be virtual for the time being to avoid due to COVID restrictions. And once things pick up safety-wise, we'll switch over to a hybrid approach with virtual events recorded at live venues with an audience. Before we begin, I'd like to briefly mention our two sponsors who helped to make this possible. First is Lighthouse Cloud, which provides continuous integration to automate your website auditing for accessibility, performance, and best practices. Our second sponsor is TechLink Resources. We are lucky to be joined by one of their representatives, Michael Johns. I'm going to briefly pass it over to Michael so he can introduce himself. Mike.
Yes, thank you, Cameron. Again, like Cameron said, my name is Michael Johns. I'm a senior technical recruiter with TechLink Resources. A little bit about us. We are a boutique IT staffing firm established in 1997. We're based in Culver City. We specialize in IT, both contract and full-time placements. Our primary clients are the large entertainment studios here in Los Angeles, but we have some, small and medium-sized clients as well. The reason I recommend you may want to, work with a boutique firm such as ours is we focus on the 3 C's. If you're not familiar with the 3 C's, these are the top 3 things that statistically people are looking for when they're making a job change. The first C is compensation, also known as cash. And people are looking for an increased compensation as a primary motivator for their job change. The second C is culture. They're looking for maybe a different work-life balance or potentially a different, team or manager. And finally, the third C in rank is career, career advancement, let's say. And either for increased responsibility or just to make an advancement in their career. That being said, if anyone is looking to make a job change potentially in 2021, feel free to reach out to me. I think my LinkedIn link is down below, and just let me know where we connected. All right. Best of luck to you in your career. Enjoy the presentation tonight, and I'll hand it back to you, Cameron.
Thank you, Michael. Hello. So before we begin, I just want to remind you that we're also on Rambly. So join us on Rambly, which you can see here is at the Cybertown Rustling, LA. It's just another form of consumption for this. It just lets you walk around with a character and you can talk and voice chat and kind of have some fun. But feel free to also join us on YouTube chat. Either way, whatever floats your boat. So we're going to begin with our presentation, which is Modern Full Stack with Rust and Writing Reliable Code. And unfortunately, or fortunately for you, it's actually me talking, so you'll have to hear my voice some more. Enjoy. Hello, my name is Cameron Manavian, and welcome to my talk, Modern Full Stack with Rust, Writing Reliable Code. Before I begin, I would love to introduce myself and our agenda for this talk. First, we'll talk about me. I'm a father and husband. I'm from Los Angeles, California in the United States. I'm a Chief Technology Officer at Libretto, a financial tech firm. I have over 15 years of experience as a software engineer and a web developer. I code to heavy metal and neo-80s music. And I have 4 cats and 2 dogs. Next, let's go over the agenda. I understand that the first chunk of the sections in my presentation may be a little rudimentary for some attendees, but I find that it will help lay the groundwork of how Rust fits into modern full stack and makes this presentation overall more accessible for all watching. First, I'll talk about what is web development. Then I'll talk about full stack development. After that, we'll cover developer operations. And then next, databases and cache. And finally, in the first half of the section, we'll finish with what makes for great full-stack developer experience. In the second half, we'll go over Rust and full-stack development, which will include the server component, the database, the search engine, the front-end code and WebAssembly, and the developer operations hooking everything together. Let's start right now. What is web development? The early stages of the web seem to have moved so slow compared to now. HTML was a pretty new technology, simple yet effective. At this time, I think we can classify most of the developers as HTML designers, or the ultra-elite webmasters. As the web progressed, tools like Dreamweaver and FrontPage revolutionized the industry, allowing for rapid creation and management of sprawling HTML-based websites. They also introduced a thing called the WYSIWYG, which is what you see is what you get, allowing for anybody to basically make HTML. Towards the end of the 90s, I think a lot of people that were HTML designers became worried by the simplicity of HTML and its gradual path towards common usage and easy learning curve, which I think was the goal in the first place. Likewise, webmasters were asking for something more. I remember this great quote from a long time ago. In the 90s, once Dreamweaver came out, I knew that anyone could make websites, so I quit my job and became a car salesman. This was actually told to me by a real car salesman after asking what I did for a living. This was from 2009. Moving on, Internet Explorer 4, or IE4, was released in October of 1997, which brought forth the era of DHTML, a fancy way of saying dynamic HTML. This was essentially the first combination of HTML, CSS, and JavaScript with a document object model, or DOM as most call it nowadays. All of this dynamic content on the front end, or in the browser, made for a great experience. Users were now able to browse websites and get unique reactions on a website using DHTML. In the mid to the late 90s, another class of tools was also gaining momentum. Server-side code was making the web a different place, and languages such as PHP allowed seamless integration with HTML. It's at this time, and perhaps ever since, that web development has been a growing industry. The primary growth of this industry is driven by money, social impact, fame, and information, and with that, misinformation. Businesses wanted to use their website to advertise and sell products to customers, and also services. So they needed to handle the inflow of traffic and keep people on the site with appealing graphics. Of course, with the growing need to brand oneself online, corporations quickly jumped onto this new internet thing. As the industry blossomed, the ever-increasing need to gain the most traffic required site creators to focus with more targeted approaches. Teams began to grow around interdisciplinary skills and roles, such as web design, which includes user interface design to maintain the brand, look, and feel of a site, user experience design, or UX, to help users keep users happy and make things intuitive, copywriting and content production to create enticing and search engine friendly text on websites, product managers and project managers to guide and maintain project velocity while also keeping the development team isolated from external politics, testers to ensure that a site is reliable, accurate, accessible, and usable, and finally, engineers and web developers to create and manage software, architecture, and servers. Now we move on to the next section. Now that we've had a little bit of a history lesson, I would like to review some of the concepts related to a full-stack web development role at most companies. What is perhaps one of the most sought-out skills in our industry, and one that some may consider fake, impossible, or downright ludicrous. A sense of humor? Nope. I'm of course talking about the holy grail that is full stack web development. If you believe in that kind of thing. What does full stack development even mean? Does it mean you can design UIs, architect scalable apps, write code, configure and run servers, or even dunk on people? The title of the person who can manage a whole website has evolved as time progresses, but in many ways their job is still the same. In 2004, I might have been called a webmaster, or perhaps the man who knows Zorro. In 2010, I was a web developer, building applications with PHP, MySQL, Flash, HTML, CSS, and JavaScript. Now in 2020, I am a full stack engineer, capable of anything and everything web-related, at least according to my family. Because a team of engineers or a company can choose what their actual stack is, there are no clear rules about what makes you a full stack developer. But anyone who can program client and server software fits the definition of a full stack web developer. Being a great programmer in general matters too. So, is full stack developer engineer unicorn a recruiter buzzword? In my opinion, it's yes and no, or maybe it depends. If you hire a developer on your team, you'd like for them to at least understand every aspect of your system. They may not be an expert on all the things, but at least they can grasp concepts and ideas. I think being full stack is the very definition of a software engineer. Does that sound a bit harsh? It might at first, but would you call a doctor a full-body medical engineer? Should all doctors be able to handle emergency situations to some degree? Yes, I believe they should. Of course, there are specialists, and this is okay. But just about any doctor could help you with an infection, trauma, or broken limbs. You wouldn't want a heart surgeon performing brain surgery, though. Personally, I feel as though there are more clear ways to identify someone's skills within a medium to large team. Yes, everyone should understand the tech and therefore be full stack, but they should also be able to settle into a role that complements the team. If working at a small company or startup, a full stack engineer will be utilized exactly as such across the entire stack. But as a company grows, a full stack engineer typically settles into more defined roles, while also maintaining their stack skill set. Many roles have a focus on the back end, dealing with databases, servers, DevOps, and APIs. Generally, these people don't see the UI at all and just look at code and databases. Some extremely handy developers are usually placed into what I call the middle stack, focused on bridging the gap between the back end and the front end. Speaking of the front end, we have developers here that are more likely to work along UX and UI designers to polish the look, feel, and branding of a website. Oftentimes, they stick around and get attuned to browser optimizations and UI features. Finally, much like the middle stack folks, we have some engineers that do a bit of everything at a given company. In this role, a senior type engineer is doing a lot of full stack work over time and is capable of making architectural decisions about any part of the application. Another way to approach this full stack terminology is to say that if you are full stack, you're probably just an expert or highly experienced. Domain knowledge comes into play here, meaning a developer can be a highly experienced and valuable person at a particular company because they know about system X, Y, or Z. They have invaluable experience within a team, and they are inherently full stack engineers, even if their title does not reflect that. But I must digress. For the purpose of today, yes, full stack developers are real, and they are people like you and me. Learn to love them. Speaking of full stack, here's a typical diagram for a web-based application. There's a front-end component that supports mobile devices or desktop browsers, a server component that supports the internal business logic and content retrieval, and a data store which holds all of a site's dynamic content. Pretty simple. But web servers aren't that easy. We need to install software, configure them, keep them updated, patch them, address security vulnerabilities, stay attuned with long-term maintenance schedules, keep our systems available, and keep them ready for users and traffic. Can a full-stack engineer really do that? I'd like to plant some ideas regarding developer operations to help see the full scope of a full-stack engineer's role at a typical small to mid-sized company. Developers and operations teams are often at odds when it comes to being nimble and secure. There is a constant tug of war between the two over how to deploy and maintain application servers. Many aspects of their jobs blur, and there's quite a bit of confusion when it comes to boundaries and requirements to deploy apps. But there doesn't have to be. Developers can adapt and pick up some of the slack of maintaining the required version and installations, and DevOps teams can focus more on security, reliability, and scale. A DevOps engineer can enable developers to better control their own version numbers and package dependencies. We looked at a basic full-stack system a little bit ago. Anyone who has done a bit of developer operations knows that there's probably some implied systems missing from this diagram. Here is just a slice of what could be more modern architecture. We have our front-end application still intact, but now enhance the detail on the server side to show all the pieces of our infrastructure. We can handle network and high loads of traffic with DNS and load balancing systems. We can offload high security application logic into a separate authentication server. And we can isolate our content into buckets to ease our scaling concerns. By breaking down our system like this, we can better scale up the highly active servers or add redundancies in different parts of the data storage systems. Of course, when it comes to DevOps, the whale in the room is Docker. Docker is one of the many ways to containerize an app in order to make it usable on many different systems. Docker is fast, it's online in seconds, it's portable, you can move across multiple types of infrastructure or cloud providers, and it's efficient, you can save money and space with it. The components of modern DevOps include the image, which is an immutable app at rest. It has all the files and dependencies baked in. A container is an instance of an image or a running image. The engine or runtime is the working node that executes containers. The registry is where you push and pull images or otherwise store them. And the control plane manages clusters of engines and containers. This all sounds pretty complicated. Thankfully, there's something that's very fancy to manage all this developer operation stuff. And we can use another great tool called Kubernetes. When you deploy containerized apps with a tool like Kubernetes, you can utilize their sets of workers to help orchestrate and manage all of your workloads with ease. Your Docker images are isolated within a worker node, which in turn store a smaller module called a kubelet, which is in charge of running a pod. Pods are one or more running containers, which is just a fancy way of saying Kubernetes can help you set up networking, services, and get your Docker images to talk to each other, or to the wider internet. But this is not just a way to sound the very loud and perhaps obvious Kubernetes bell. Instead, I also want to mention that we can certainly use a Rust Docker image, which has an OS and compiled Rust binary of our application ready to go within a container on Kubernetes. You can also run a special type of kubelet called a crustlet. A crustlet is a third-party complement to kubelets. A kubelet can run a portable application in the form of a Docker image, but a crustlet can run a portable WebAssembly binary, which can run on any hardware. It should be noted that you can't replace all Docker images with crustlets that use WebAssembly, but it can handle some other things pretty efficiently. We won't be covering this too much today, so I just wanted to call it out real quick. Now that we figure out how to transport our apps in a common format with a reliable and standardized technology, we can focus on the last bit of a full-stack engineer's job, the data. In this section, we'll review some common practices related to databases and cache used in full-stack developers' daily workflow. What do we do to keep our data reliable, secure, and scalable? Here, I've selected a picture of a dog. For some, the dog might be the protector of the data. For others, they may interpret him as the data to keep safe behind the closed gates. Keep your animals out of harm's way. Or finally, if you're afraid of dogs, I apologize, but perhaps you are the data and the dog is kept away from you. I think this dog looks pretty friendly though. At its core, regardless of which database systems we choose, it's easy to think of them as some hard drive out on the internet or in the cloud. We can save vital information about our apps or our users or a product in a database to keep things safe. There is also, of course, NoSQL. They are a cousin to SQL databases like MySQL, but not related. That was a dad joke for my kids. We don't need to discuss the merits of NoSQL versus relational databases, but generally it's desirable to use them for their strengths. Many projects utilize both types for different portions of their data needs. To go back to my earlier simplified view of a typical application, we can see that the database is utilized by the server in order to retrieve and collect data to be presented to the user on the front end. In that regard, many architectures opt to include a cache layer to improve availability and scale. Often this is accomplished by a memory database such as Redis or Memcached. Using such systems, we can give our server application a quick boost to performance by adding a thin caching layer at an object level to improve query times and decrease server loads. In this diagram, we can see that we start with a request, and we check the cache. If it's in the cache, we can just simply return the cache data and save our database the hassle. If it's not in the cache, we can retrieve the data from the database and then cache it, and then also respond with the same data. It kind of creates a quicker version of the same data. Our next section is about the developer experience while building apps in a full-stack framework. Before we can truly talk about developer experience, I'd like to briefly mention the notion of a 12-factor app. This methodology is designed to give engineers a roadmap and checklist for building software apps and services, ensuring longevity and reducing software rot. In some languages, a true web application framework is not readily available or not very mature. Some of them might call themselves lightweight or flexible, much like a house that only has a frame. It might have the walls, the roof, the foundation, but it's up to you to pick the floors, interiors, and add the electrical and plumbing. Of course, if I want to build a basic structure, I can get a house-like frame, add my own walls and roof, and call it complete. Since there are no doors or windows, I don't need to cover them up, so I remain flexible. Likewise, if I want a simple web application, I can pick up a lightweight framework and add only the exact features I want, perhaps just JWT authentication and a simple MySQL server with no ORM. If I want a house with a kitchen, a dining room, 2 stories, I'd probably opt for a more defined structure that affords the quicker building of these amenities. Likewise, if I were to build a more robust application using a full-stack framework, I probably want one that is slightly more opinionated and rigid, which in turn affords me the ability to build bigger applications faster because I can focus on the end implementation instead of the nuts and bolts. So when it comes down to it, there are about 2 paths when selecting a framework to use in your project. The first is lightweight, sometimes called micro-frameworks, like Express, Sinatra, or Silex. These allow developers to build the exact app they want, adding in features as needed. They often are more like a big library of tools that let you easily add in custom logic at any layer. And since they're not focused on adding features, these frameworks are generally faster. That being said, there are some negative aspects as well. Engineers will probably end up writing more code overall as the app grows. There are more things to configure, set up, and possibly break. And finally, adding that simple feature might be a lot more work than had you selected a more robust framework. The other type of framework is usually called opinionated or sometimes batteries included. These are things like Sails.js, Rails, or Cake.php. They allow developers to build feature-robust apps with unit tests and boilerplates abstracted away. They allow you to get things that just work because they follow conventional best practices such as file names or method names. Since these frameworks are feature-rich, they usually come with support for automagical API and DB code to create read, update, and destroy data, or CRUD. There are some cons though. Since there are a lot of features, you may have to wait for long installs for all the dependencies of the application. You sometimes have to have slower performance because there's a lot more things to disable or turn off to speed up the server. And in a few instances, even for myself, it's sometimes hard to customize, so you end up wasting tons of time just trying to add a simple feature that goes outside the opinion of the framework. Whether one chooses a lightweight or opinionated framework, the expected features are usually about the same. We want it to be fast. We want it to be extensible. We expect intuitive routing and parameter extraction. We expect form data handling and JSON friendliness. We expect static file support and correct support for HTTP and possibly WebSockets. We expect access logging, and we expect some sort of database connectivity that's also injection safe. Of course, opinionated frameworks often add extra icing on the cake. They might have a view layer that returns HTML. They probably have model view controller. They probably have some way to make CRUD very quickly with APIs and databases. They might have GraphQL built in. They might have database ORMs to help you map out your data. They might have streamlined authentication checks with authentication servers or JSON web tokens. They also might have authorization checks to prevent unallowed access to resources. They might support asset and organize your static assets like CSS, JavaScript, and HTML. And finally, they might have all the other kitchen sink features like email, database migrations, and what have you. So is Rust web yet? Many people say yes, but I think there is a lack of opinionated frameworks. The reason an opinionated framework hasn't been seen quite yet is because it's hard to build one. It takes a large team to build one. I don't think there's anything out there on Rust to replace Rails, CakePHP, Django, or Sails, but one can definitely say that lightweight frameworks have reached a great level of maturity in Rust. In the next half of my presentation, we're going to build out our thoughts on full-stack web development and build a greenfield Rust application using a lightweight framework in Rust. Rust and full-stack. Our Rust application will be a bare-bones used car website, which will list the latest used cars and their prices, and also allow users to search for specific cars within the database. Our goal is to build a Rust web server that connects to MySQL, caches in Redis, leverages MeiliSearch, and uses React in the front end with TypeScript and Rust WebAssembly binaries. We'll also get some help along the way with Webpack, Docker, and Kubernetes. Our front-end web application contains a handful of files organized in a typical React convention. It has Rust via WebAssembly and uses WASM-Pack to help build out some type-safe number crunching. To save time, I've also used Bootstrap for the UI component library to give an extra visual flair. Our backend application only contains 5 files. The main file is the entry point and will set up the web server. And inside of the car module folder, we'll look at some easy ways to set up a CRUD with MySQL, cache with Redis, and search with MeiliSearch. First, we'll explore the web server. With Rust, the options for backend servers are thankfully widely available. Actix jumps out as a top candidate as they provide a powerful lightning-fast framework for building web applications with Rust. As a matter of fact, it recently ranked second overall in a Tech Empower Run benchmark, losing only to Drogon, a C++-based web framework. Considering that Actix is first and foremost focused on safety over benchmarks, placing second is fine with me. Our Rust web server will use Actix as the core, which is a lightweight or micro framework. Actix makes it super simple to start writing web servers. Here I am able to specify the path and the permitted method as git / using that macro at the top of the file. This limits unsupported requests to the server's index route. In our reference app, we can quickly set up an HTTP server and configure common pieces of our full-stack application in one place. Here I create the server. Next, I can assign data resources to the app's data extractors with MySQL and Redis databases. After that, I can drop in my create, read, update, destroy methods from other abstracted modules and pass them into a configure method to connect them to our web server. We'll take a look at this module in a little bit. Finally, we can serve static assets, which I've done last to ensure minimal collision to the other server routes above. This will grab our front-end application, including our WebAssembly files. Let's take a look at the model layer of this application. For the database layer, I've opted to use SQLX, as it is a pure Rust-based SQL crate that features great async support and compile time checked queries. The compile time query checker is extremely powerful and lightweight, allowing for type check SQL strings while you're editing code. But what does that even look like? Here I purposely break my code a little bit to show off the powerful feature in the SQLX macro. First, I change the car struct price property to signed 32-bit number, which results in a compiler error for a type mismatch against the database. Price should be unsigned. Next, I remove the selection of year from my query, which then creates another compiler error when I try to use the query result later on. I think this feature alone is phenomenal, but the crate is also 100% safe code and works with PostgreSQL, MySQL, SQLite, and MS-SQL. Our schema for the database stores each of the desired attributes of a used car, such as price, year, make, model, mileage, color, and the state within the US the car is currently located in. Next, we create a struct in our Rust model that mimics the database columns exactly. Our data itself comes from a Kaggle dataset that has over 2,500 cars listed with various attributes, which were imported into our MySQL database. The implementation for this example allows users to read from their database, whether it be to find all cars or to find any cars by an ID. I opted not to implement the other types of CRUD features. As part of our contract with Actix, we also need to implement a responder trait for the car struct. The main purpose of this is to define the expected response of this particular struct, which in our case is just JSON. Using SQLX and Actix, we've fairly easy wired up a backend server that can retrieve content from the database and send it over HTTP in a JSON format. Here is our front end pulling data via JSON fetch from the web REST server. It's a little slow, as it's retrieving 2,500 rows of data each time a user clicks that button on the front end. Let's take a look at the web server routes and see if we can improve some things by caching MySQL in a response for a short period of time to reduce the server load. So let's look at the routes layer. Within our cars module, inside the routes file, we have a couple of functions that pair with our model functions. For instance, this is the function that is called when our API requests the /cars route, and it returns back a list of cars as JSON, utilizing our model function you see there, car find all. Each time the user clicks that car load button on the front end, it retrieves the fresh data from the database. Chances are the database hasn't changed that much frequently, so we can add a thin layer of cache to improve performance right here at the route level, a common practice. Going back to our earlier slide, we want to first check the cache, and if it exists, return it. Otherwise, grab the data from the database, cache it, and return the response. A similar flow can be handled on the outside of the server using something like Varnish, which is another technology. But I find that application-level caching rules give the application developer themselves more control and less mystery about what the DevOps team is doing with the cache. Here we've now updated the function to handle the cache just as described. I've collapsed the code a little bit to show the high-level flow. First, we check the Redis cache using the git command with Redis. Then we convert our Redis result into an option, where it's either some data with cars in it that we can immediately respond with JSON, or none, mean that there was either an error or no data in Redis. If we match with the none, we can just pull the data from the MySQL database using our model function car find all. And then we also want to wrap up and save that fresh database data into Redis with a set and expiration command. This data will expire in 300 seconds, or about 5 minutes. And then we need to remember to send the DB data through the response as JSON at the end of this second half. Here we can see the response improvements by just adding a simple object cache later, using an in-memory store like Redis. The first request on a cold cache results in a response time of 180 milliseconds. The subsequent requests all benefit from Redis's memory and save more than half the time. This allows us to scale our services across more users and also shave down time and cost. Let's now look through the search engine. Adding a search engine gives an extra boost to a web application's usability as it allows the user to find exactly what they are looking for. Within the Rust ecosystem, I have found great success and joy with MeiliSearch, a Rust-based search engine that has many similar features to Elasticsearch, but comes with some smooth setup out of the box. Why MeiliSearch? Well, like I said, it works out of the box with any configuration. It's very fast. It uses a conventional setup to avoid the schema headaches of typical search engines. It's Docker friendly. They even have first-party Docker images. It's typo tolerant. And it has great first-party clients for Rust, JS, and many other popular languages. To show off how easy it is, here's the search engine indexing script. For anyone that has ever mucked around with Elasticsearch, you can see how elegant this is. First, we create an index in the MeiliSearch engine. Then we retrieve data from the MySQL database. Next, we map the database into a vector of car structs. This code is the same as the one within the car model, by the way, but I just copy-pasted it here for clarity. Finally, we send that data off to MeiliSearch to start indexing, and it's usually available within seconds on the publicly searchable interface. This function is called as part of the Rust web server startup sequence as an example, but you would probably want to offload this into some sort of Kubernetes cron job. Here's a demo of the search feature on the front end. I put it into modal just to make it easier, but you can see that searching through it is near instantaneous and provides back more of the filtered cars that you want to look at. On the front end, we have a fairly typical React application that handles basic user interface and form handling. Of interest is a utility function that allows us to send over 2,500 rows of card data into a Rust function to allow it to run type-safe computations on it. In the Rust file, we have our same struct here, which I lazily copied over, but I could have also imported. Here's the output struct that the front-end TypeScript is also expecting. In our Rust function, we operate a type-safe computation that sums up and averages price, year, and mileage for all cars and then returns them back to the front end as a car stats object. Here it is in action. Once the user loads the list of cars, a new button appears that says Compute Averages with WASM. This button will take the current list of 2,500 cars and send it over to our Rust function. Once the Rust function computes the average, it'll return it back to the JavaScript code, which allows React to render the results. The final step in our epic full-stack launch party is to deploy our app somewhere. That somewhere is going to be Kubernetes. We want our app to be deployed securely, efficiently, and easily. Here's what our full-stack app build will look like after it is containerized and running in a Kubernetes cluster. We can use any cloud provider that is Kubernetes friendly and deploy a single Kubernetes cluster, which will hold our Rust web server that connects to MySQL, caches data in Redis, leverages MeiliSearch, and hosts its own React TypeScript WebAssembly front-end application. Normally, you might consider using the cloud provider's offerings for things like a database, as it affords you replication and automated backups for a small extra price. but in this example, we are keeping everything close by. We already know about the internal systems a little bit that are represented with pods in this Kubernetes cluster. Let's look at some of the outside stuff I've added. A load balancer here helps us distribute our traffic across multiple zones and servers to allow evenly managed resources and scale up and scale down events, to also help our app grow and shrink with traffic. Ingress helps Kubernetes route external requests to their desired Kubernetes service, in turn to serve traffic to the correct pod. Ingress can also handle a few other things like TLS certificate management and path routing to serve different apps on different paths. We configure a modest cluster, and then we set up our Kubernetes config. First, we create persistent volume claims, one for MySQL and one for MeiliSearch. A persistent volume claim is important for data as it means that if a container or pod dies or restarts, our data associated with it doesn't go down. For MySQL, this means all the actual raw file system data and the index data. For MeiliSearch, this also means the generated index data. As noted before, the MySQL within a Kubernetes cluster is bare bones. If we want to ensure automated backups and replication that's cost-effective and safe, I'd opt to use the cloud provider. Now we create a deployment for our Kubernetes cluster, which just provides a declarative way to update our pods and describe a state. And the deployment controller will handle the setup and teardown as well as auto-scaling. In our system here, you can see 4 containers, the 4 that we've talked about, our full-stack app, search, Redis, and MySQL. If we dive into the container spec for the primary Rust web application server we've created, you'll see a number of things I've configured. The Docker image to use. Here it is being stored privately within GCP's container registry, but they can come from anywhere. The container service port. The desired resource allocation for my application. And a readiness probe that will attempt to communicate with the server on the desired port and the path to determine if an app is ready to start or if it's failed. If we briefly glance at the search and Redis container specs, we can also see similar concepts. For both, we specify the image name and optionally a version. And Kubernetes will look for these Docker images on Docker Hub for us automatically. Another thing to point out here is that we choose to mount the persistent volume that contains the search engine index data for MeiliSearch. In the service config, we select the full-stack Docker container, target it by port 2020, and then expose it under a Kubernetes service with a more standard port of 80. We also do the same with the search engine, allowing MeiliSearch to handle traffic directly. We can configure the ingress to decorate a load balancer with a TLS certificate to ensure all traffic is sent over HTTPS. This is done with the help of a thing called a cluster issuer, which allows a system like Cert Manager to automate TLS renewal with another system called Let's Encrypt. And last but not least, let's look at some automagical Kubernetes fun. Here we are able to send search traffic to the relevant pod that handles MeiliSearch and send the rest of the data to the web server. The key here is the path property, which designates the rules to track the correct traffic to the correct server. This allows us to send search traffic to the right pod. Our Rust app is now deployed with TLS on a Kubernetes cluster, and it's ready for traffic. You can see the live app at fullstack.cameronmanavian.com, which also includes a link to the GitHub repo. That's it. I hope you enjoyed the journey. I know it was probably a little tricky here at the end as there are a lot of things to look through, and I appreciate your patience. I also hope you enjoyed the first half of my talk, which talked about full stack web development. All right. Well, thank you very much for joining me. I know it's been a long talk because it was mostly about full stack development and not about Rust as much as I'd like it to be. But this was our inaugural, first ever Rust Los Angeles talk. I'm just trying to start this community up because I was kind of missing out on Rust in Los Angeles. So I'm trying to collect a bunch of speakers for the rest of the year, and that includes people like you in the audience. We're looking for speakers right now, and every speaker gets cool swag, including some Rust sunglasses, a nice Ferris Rust Los Angeles sticker, and if you do a 25-minute speaking gig or 40 minutes, you get either a free book, or I'll donate money to a Rust open source project of your choice, or I can give you an Amazon gift card. And the only reason I'm doing that is because I want to help the Rust community grow, especially in Los Angeles and just overall, because I love Rust. Thank you for joining me. I'm going to hop on to Rambly, but I'm also going to, if anybody has any quick questions on the stream, feel free to ask them now, and I can answer them on the video instead. I know there's a time delay as well, so. If not, I'll just hop onto Rambly, which is, again, it's optional. I'm hoping that maybe mid-year this year we'll have less COVID restrictions because we have a vaccination. And who knows, maybe people will finally get clear and hopefully everything works out. So see you guys on Rambly. Otherwise, have a great night. And this stream will be available as a video for on-demand right after this. Oh, thank you, Alan, for your comment. Oh, but yeah. I'm going to hop off here, and I'll see you guys on Rambly if you join. Later.